Time has played a very important role in our development as a species. Ever since we first became aware of its passing, it has since grown into a commodity that we feel that we have ownership of, but we don't really have control of it. We even use language such as owning it, being able to spend it, being able to receive it, give and take it. And in fact, Benjamin Franklin actually aligned time with value and gave it money. And that is in complete contrast to the view of Einstein that said that time is actually an illusion. Now, these two ideas are two that I would like to explore over the next talk that I give. Now, the first question I want to delve into in order to understand this is actually this one. How do we experience time? Now, in order to do that, I'm actually going to take us into a little world of physics, so enjoy it with me. The first view that I want to go into is actually relativity, and the first implication of relativity that Einstein came into. In order to do that, I'm going to introduce us to two characters. The first person is a businesswoman, so say she's working in LA, and the second character is an astronaut up on the International Space Station. So if we take our experience of the day, we wake up in the morning because our alarm clock says so. We then go and we get our coffee, getting ready for the day. We suddenly see in the corner of our eye the time. It's like, oh, we've got to go to work now. We then travel to work. We get to work. We get there a little bit late. We say sorry. We then get another coffee. We then start going about our day. It tells us, oh, it's a break time now. Oh, we can have lunch. And then it tells us the end of the day. We get to go home. We cook our dinner. The clock even tells us how long the chicken's in the oven for. And then it tells us, okay, it's a little bit late. You should probably go to bed now. You've been watching Netflix too long. Okay. Now, that regulation of our day is very important. The same regulation of our day is important if we are an astronaut up there on the International Space Station. We need to know when to wake up, when to do our tasks, when to then go to bed. They don't get the same experience of the day that we do, 24 hours, the sun rising, the sun setting. They go around the Earth every 90 minutes. So they get a sunset and a sunrise every 90 minutes. So they need to know the passing of time. Now the problem is, if we have a clock and we send it up, and in a very simplistic view, we look at the passing of time, what we actually find is that when we're up on the International Space Station, time passes a little bit slower. Now that gives us one very important implication of relativity, and that is that our position in the universe is important. And in fact, the stronger the gravitational field that we are in, the faster we experience time. Now, if we then take the second idea of relativity, and in order to do that, what we're going to do is we're going to hop on a London tube. And let's say actually, when we're on the tube, it's night time, so they've dimmed down the lights. What we then do is we take out our phone and put on our torch. Now, what we can actually process in our brain is that the light ray passes from our torch, travels down through the carriage, hits a part of the carriage at the end, and it travels back to our eye. Now, in our brain, we actually know that light travels a certain speed. And we know the distance, and the distance it comes back. So our brain registers that, and it tells us how long it takes. And that's from a very simple equation, that speed equals distance over time. If we know the speed, and we can gauge the distance, we know the time that light took to do that. Now, as we're on this tube and we're passing along, we're going through stations. And let's say that on the side of one of these stations is a woman. Let's call her Brenda. She's standing there, she sees this carriage passing. And what she sees is our torch. And she sees the light traveling along, hitting the same part of the carriage and bouncing back to her eyes. But to her, the light has had to travel further to catch up with the end of the carriage, and therefore come back. Now, in her brain, she knows the speed of light. It's exactly the same as the speed of light that we have. But she has seen the light travel a further distance. Using the exact same calculation, what we actually find is that to her, it looked like it traveled a longer distance at the same speed. It has now taken longer for the light to do that. These two events occurred at exactly the same time and finished at exactly the same time. And what it is telling us is actually that we, on the carriage, experienced time passing faster than she did. She saw it taking a longer time to occur, which gives us our second implication from relativity, and that is that our motion through the universe is important. So we've now got two ideas. Our position in the universe is important for how we experience time, but so is our motion through the universe. Now I want to give you a third and final bit of physics here, and this is entropy. Okay? Now this is a very complicated idea, entropy, but I want to try and make it simple for you. So what we have here, on the bottom left, you can see a young girl, and let's say that she is there blowing bubbles. Now, as she blows bubbles, the bubbles get formed and it floats around in the room based on the random motion of air. Now, what that is telling us is that the universe is trying to spread out these bubbles. Now, why? Why is it doing that? It is doing that because the universe has a fundamental law about it, and that is it wants to take all energy and spread it out. Now, let's say, actually, we want to try and reverse this process. So what we do is we take those bubbles and we try and move them back together again. So you have to reach out, grab one, bring it in. Reach another one, grab one, bring it in. And as we do that, what we are having to do is actually expel energy to do that. Now, we have to put work in to go against what the universe wants to do. And that is another fundamental idea. The universe is always trying to increase entropy. It wants to spread everything out. It explains why my desk at work is an absolute mess. Now, this is because the universe is taking energy and spreading it out. Now, if you take that back to the beginning of time, the Big Bang, what happened ever since then is the universe is spreading and expanding, trying to spread the energy out. And that tells us the direction time goes. Time will always flow in the direction in which energy spreads out. So there are three key ideas. Our position in the universe is important. How we move through the universe is important. That tells us how we as individuals experience time. But we always feel time flowing in one direction, forwards. We always go from young to old. We never go back. Benjamin Button doesn't actually occur. Now, my second question then, now we have a slight understanding of how we experience time, is to look at why is it therefore important to us? Why is time important to us? Now, if we go all the way back to the Stone Age, when Stonehenge was actually built, back then, the passage of time that was important to us was the seasons. All we cared about was when was spring, when was summer, when was winter coming, when do we do the harvest, when do we have to sow our seeds? But if you come forward, we then invented sundials, and we tracked the passage of time across the day. When was sunrise? When was sunset? Throughout the day, when was the middle of the day? As we came forward again, we invented the clock. The passage of hours was important. And then we soon get to us now, and we have atomic clocks. We have electronic clocks. We track ever more shorter periods of time. And that gives us the passage of time available to do our GPS, to do our computer processing really fast. Now, I want to give us a little sort of story to go along with that, something that we have ourselves experienced. So what I'm going to take us on is a little sort of story through messaging someone. So let's say I've got a very attractive lady in my phone. Call her Charlie. Now I want to meet up with her, so I'm going to send her a message. So I and ah about it, and I go throughout the day and I'm like, oh, I'm going to message her now, I'm going to message her now. Eventually I sit down and go, I'm going to do it. I'm going to message her. So I write her a little message. I make the big decision. Do I put an emoji at the end? Yeah, I do a nice cheeky message, put a little wink at the end, see if I can get a date. I send it. I get the one tick. It tells me, yes, the message has sent. I get the second tick. Yes, she's got it. I'm then waiting there going, okay. Oh, blue ticks. She's read it. I'm then waiting. She's read it. Why isn't she replying? Maybe I shouldn't have put the emoji there. I really shouldn't have done. Oh, she's sending me a message back, and then I get the response. All of that, because I programmed it into this, I know it took 24 seconds. But that was really traumatic between sending the message and receiving the reply. Now, that shows us just how skewed our view of time has become. 24 seconds, and we were umming and ahhing, we were thinking about the next day, the next person we were going to message. All of that, though, is what we experience now. But if we go back 100 years to 1920, imagine we were doing that same thing then. We would and ah about what we were going to put in our message. We'd come up with a poem or something, write it down on a piece of paper, put it in an envelope, put a stamp on it, put it in the letterbox. I'd have to wait a week to get the response that, yeah, we can go out for a drink next month. But now, I send that message and I'm waiting 24 seconds questioning my life decisions before I get the response and go, yeah, okay, we're going on a date. Now, all of that, why is our vision of time so skewed? And it all comes down to this, the idea that we have more transistors now than we ever did before because we invented computers, we put more transistors, we got faster and faster and faster and faster machines. Also, we have faster and faster internet. When I was younger, I remember loading up Google and it used to take ages and we get a layer of pixels all the way through. And then I'd have to really question what I was going to type in and whether it was worth waiting 20 minutes to get the actual information. Now I can look up anything I want on my phone, no matter how trivial. Now, I'm going to take this into another realm, and that is trading on the stocks. What I've got here on the screen is the stock exchange there on the left-hand side. Okay? We've connected it up with the wire to two computers. Okay? Now, what happens is we've got a change in prices in the stocks, and that signal is sent down the wire. And as it travels down the wire, it gets to the junction. The signal goes to the nearest computer first. We get the information. Then the later computer gets it a little bit later on. Now, if I am in an office that is closer to the stock exchange, I'm able to respond to that price change faster. I can therefore trade my stocks before it plummets or buy something before it skyrockets to then sell it later. Whereas someone further away, they have to wait half a second before they can do that. Now, all of this means that we actually have different prices in the rental properties of offices. So the further one would be cheaper. But if I was closer to the stock exchange, it would be much more pricey. Now, this can be seen in the New York skyline if you're looking at lower Manhattan. And I've actually got a few pictures here going over the last 100 years looking at the skyline of Manhattan. I go from the first one, there's only a few high-rise buildings all around the stock exchange. But as we go forward and we go forward through time, what we're finding out is more and more office space is being built closer to the stock exchange. And here you've got a sky view image, and you can see this cone of taller buildings all around the New York Stock Exchange. Okay. Now, this idea that we have to be closer to the stock exchange in order to make more and more profit actually went to some very weird place very recently. Now, what happens is we have this new thing because of our faster computers that we were talking about called mass trading. You can trade thousands and thousands of stocks very quickly just with the press of a button on a computer. You can write programs to do the trading for you. Now, and that means we can make massive and massive profits in very short periods of time. And if we were trading, let's say, in Chicago rather than in New York, you would need to have a really fast connection. So you used to have optical fiber connections that used to zigzag all the way around the country to get to Chicago. Then companies put mass investments in to be able to make it straighter and straighter and straighter. Now, a straight path is as straight as you can get. So once you've built this straight path, that's the quickest any signal can ever get from New York to Chicago. However, back in 2011, a scientist actually put out there that they found a faster than light particle. They thought it was a neutrino that went faster than light. So suddenly we now have a way of getting a signal from New York to Chicago faster than light can travel, which was how we use our internet. But literally 4 or 5 months later, they had to put out that actually this was a false detection. They weren't actually detecting faster than light neutrinos. Now, in that time, companies had invested millions of dollars trying to look into whether or not this was actually a feasible way of sending signals from New York to Chicago. Now, that just shows how skewed we are. We're trying to fight over milliseconds of time. Remember, if we go back in time, the passage of the seasons was what was important. Now, it's milliseconds, it's nanoseconds, and even shorter than that. Now, my last idea, now we've got why is it so important to us, it's because actually time is money, is to look at, well, what actually is time? Now, time is just the way that we track the passage of events from one to another. Okay? Now, if you ask a geographer will look at the lattices in rock, and they would say, yes, that's the passage of millions and millions of years. So to a geographer, the passage of millions of years is important. To me, I just look at that and go, oh, that's a pretty picture. We get lots of nice different color rocks. Okay? If you were to ask an astronomer what's important, why is time is important, what is the passage of time, they might think, well, let's look at one particular picture. Now, this picture, if we took the Hubble Space Telescope and we pointed it out into space at an area of the sky 1/10 of the size of the full moon, what you would actually look at, and you stared at it, it's this blank piece of sky, you'd stare at it for months and you would get this picture. It's called the Hubble Deep Field Image. Now, in this image, I've got it zoomed in on the right-hand side there, is the most distant galaxy we've ever seen. About 13.5 billion light years away. That means the light left it 13.5 billion years ago, and it reached us today. And that is the furthest galaxy we've ever seen. Now, in this picture as well, if you just look at all of the dots in that image, what you actually see is galaxies, all different distances away. And we're seeing layers and layers of time. Now, geographers look at layers of rocks, that's millions of years. Astronomers look at that one picture and they see layers of galaxies showing the tracing of billions of years. So, to an astronomer, it's not nanoseconds that is important, it's billions of years. Really big difference in time there. Now, my last little bit is this. Imagine I had a graph. Okay? Physicists love graphs. I have time and distance. So I have time on a y-axis and distance on an x-axis. Let's put us at the middle, because we are very egocentrical species. We are at the center of everything. So I've put us at the middle of this graph. And I then trace out a cone. Now the cone, it's called a light cone. It's everything we can see because light has taken time to travel to us. And that cone is showing everything that we can see. Now imagine there's an event. This event occurred outside of our light cone. It's further away than we can actually see. Now this event, let's say, occurred 15 billion years ago. Now we won't actually be able to see that until light has had time to reach us. So this event that occurred 15 billion years ago will actually reach us sometime in the future. Now that brings a really weird sort of view into our head if you think about it. Something that occurred a long time ago will not occur to us until the future. So that means the past is actually the future. And that is a really weird view to have of the world, which is something that I want to just leave you with. And that is, what actually is time? Well, time is just a measure of the largest distance between two places.